Welcome to MRL. In this learning session, let us learn the solutions of the examples of exercise set 3.5. But before we proceed with the solutions, what I suggest is please go through the playlist of World of Numbers, learn the basics, learn the fundamentals, and then apply that knowledge in solving the examples. So let us proceed with the solutions of exercise set 3.5. Now here we are given three rational numbers 7 by 20, 4 by 15, 13 by 250. We have to find out the type of decimal expansions of these rational numbers, but we should not find the decimal expansion by long division method, but by finding out the factors of q in p by q. That means we have to find the factors of 20, factors of 15, factors of 250, and then decide the type of decimal expansion. Now before we proceed with the examples, you have to remember that if p by q is a rational number, and in p by q, if the factors of q are 2 raised to m, 5 raised to n, or 2 raised to m into 5 raised to n, or 10 raised to p, then p by q will have terminating decimal expansion. Or else, if the factors of q are not 2 raised to m, not 5 raised to n, not 2 raised to m into 5 raised to n, or 10 raised to p, then the p by q will have a non-terminating repeating decimal expansions. As you already know, the rational numbers can have two types of decimal expansions. One is terminating, the other one is non-terminating recurring decimal expansions. So let us see how to find out the type of decimal expansion with the examples here. Now we are given 7 upon 20. Now 7 upon 20, first of all check whether 7 and 20 are co-primes. Co-primes means 7 and 20 should have a common factor as 1, and 100% they are co-primes. So now write the factors of 20. Factors of 20 is 4 into 5, 4 into 5 is 20, 4 is 2 square, and 5 is 5 raised to 1. Now you find the factors of q, that is 20 here, are a product of 2 raised to m into 5 raised to n form. That means it is 2 raised to 2, 5 raised to 1. It is of the form 2 raised to m into 5 raised to n. And we know that if the factors are in the form 2 raised to m into 5 raised to n, then the rational number will have a terminating decimal expansion. Therefore, 7 by 20 has a terminating decimal expansion. Now we can verify that by long division method. So divide 70 by 7 by 20. So when we divide 7 by 20, we get 0.35, and which is 100% a terminating decimal expansion, and that is what is the method of showing or finding the type of decimal expansion of the given rational number. Now let us go to the next example. Now we are given 4 by 15. Again, 4 and 15 are co-primes. The common factor between them is 1. First you have to check that. Then write the factors of 15. Factors of 15 is 3 into 5. And 3 into 5 is 3 raised to 1, 5 raised to 1. Now you find here q is not having the factors of the form 2 raised to m into 5 raised to n, because 3 is 100% different from 2 and 5, and therefore this rational number 4 by 15 has a non-terminating recurring decimal expansion. So please remember this. If the factors of q are different from 2 raised to m and 5 raised to n, definitely it will have a non-terminating recurring decimal expansion, and we can verify it by long division method. By long division method, we find it is 0.266, and 100% it is 0.266. It will repeat, therefore it is 0.26 bar. The decimal expansion is non-terminating and recurring decimal expansion as far as the rational number 4 by 15 is taken. Now if you take the next rational number, that is 13 by 250, again the common factor is 1 here, therefore 13 and 250 are co-primes here. Now the factors of 250 are 25 into 10, that is 5 square into 10. It is of the form 5 raised to n and 10 raised to p. That means it satisfies the condition, and therefore the factors of q satisfy the condition 5 raised to m into 10 raised to p. Therefore 13 by 250 has terminating decimal expansion, and we can verify it by dividing 1300 by 250. We get 0.052, and therefore it confirms that the type of decimal expansion of 13 by 250 is a terminating decimal expansion. So please remember that. Now the second example of the exercise 3.5, we are given 1 by 13. We are given 1 by 13. Now what we have to find is decimal expansion by long division method, and also find the repeating block. Okay, we have to find the repeating block and then evaluate further 2 by 13, 3 by 13, 4 by 13 and find out the decimal expansion of, therefore we have to find out the decimal expansion of 1 by 13 and also find out the repeating block and also find out whether it exhibits a cyclic property or not. So let us understand, it has got many parts in it. So let us go one by one. So let us find out the decimal expansion of 1 by 13 by long division method first, and by long division method we find the decimal expansion is 0.076923, which again repeats, therefore it is a non-terminating repeating decimal expansion. So the decimal expansion is non-terminating and recurring or repeating decimal expansion, and the repeating block, since I have put a bar on the top, it means the repeating block is 0.76923. that means this is the repeating block 0.76923. so 6 digits repeating block it is. So if you see 1 2 3 4 5 6 digits repeating block. If you want to find 2 by 13, then you multiply 0.76923 by 2. That means when I multiply 0.07693 by 2, I'll get 0.153846. And if you want 3 by 13 multiplied by 3, we get 0.230769. If you want 4 by 13, multiply the same by 4, we get 0.307692. So therefore remember that 1 by 13, 2 by 13, 3 by 13, 4 by 13 gives us a non-terminating recurring decimal expansion with a repeating block of 6 digits okay. And also remember that 1 by 13 has got a decimal expansion of 0.076923 here, and here it exhibits these blocks. If you study, they will exhibit distinct cyclic property. There is no doubt about that. It exhibits distinct cyclic property, but there are two different cyclic properties here. If you take the first one, that is 0.153846, if you check this and this, okay, if you check this and this, that is 0.230769, 0.307692, there is a repeating block here. It starts with 0.230769 and start with 3 here, 30692. So you have the cyclic property here, and this will exhibit the cyclic property. This will exhibit the cyclic property with 4 by 13. So therefore we have two types of cyclic properties. So it shows a cyclic property, all right, but it shows two types of cyclic properties. There is no one cyclic property here, there is a second cyclic property also. Therefore there are two distinct cyclic properties. When you divide 1 by 13, that is n by 13, n is 1 2 3 4, there is there are consecutive numbers, n by 13, so shows two distinct cyclic properties. So please remember that. So therefore remember that after finding 1 by 13 by long division method, multiply the value of 1 by 13 by 2, 3 and 4 to get the values of 2 by 13, 3 by 13, 4 by 13. You will get them, and also check the cyclic properties. There is a dual cyclic property. Two distinct cyclic properties are exhibited, and that is what you have to identify here. So please remember that. Now coming to the next important study, that is the third example of the exercise. Now we have to find out the given number is rational or irrational. Again I'll repeat, you are given a number, you have to find out whether the given number is rational or irrational. So let us understand that. Now the first number is square root of 81. Square root of 81 is square root of 9 square, and square root of 9 square is 9, and 9 is a rational number. Therefore square root of 81 is a rational number. Take the second one, square root of 12. Square root of 12 is square root of 4 into 3. Square root of 4 into 3 is square root of 4 into square root of 3. Square root of 4 is 2 root 3, and therefore 2 root 3 is a product of rational and irrational, 100% irrational, and therefore root value is irrational. Now 0.333 is a non-terminating recurring decimal expansion, and therefore it represents a rational number. 0.3 bar is a rational number. Now if you take the next example, 0.12345, 12345, 12345, that means 12345 is a repeating block, and therefore it is a non-terminating recurring decimal expansion. Again it represents a rational number. Now if you take the fifth example, 1.01001, it continues like that, unending, and if you find it is a non-terminating, non-recurring decimal expansion, and therefore it represents an irrational, therefore it is an irrational number. Now if you study this one, there is 23.5601856, and it is ending. Since it is ending, terminating, it is a what you call terminating decimal expansion, therefore it represents a rational number. Therefore this is a rational number. So please remember that. Now the next example, that is 3b, to find p by q form of the rational numbers. Please understand here, we are given a decimal expansion, you have to find out the p by q form of this. Now let us understand this. Now what is the decimal expansion given here? 0.3333, it is a non-terminating what you call the non-terminating recurring decimal expansion, or 0.3 bar. It is 100% a rational number. Now to convert this into p by q form, let us assume that x be equal to 0.3 bar. So let x be equal to 0.3 bar, or x is equal to 0.333. Now bring this 3 to the left, make it a whole part, or make it the integer part. To make it an integer part, then I have to multiply by 10 on both the sides. When I multiply by 10, I get 10x, and this becomes 3.33 dot dot, that is unending. Now 10x minus x, subtract the x from 10x, we'll get 10x minus x. That means you have to subtract 0.33 from 3.33. So 0.33 will cancel out. 3 minus 0 is 3. Therefore 10x minus x is 9x. 9x is equal to 3. X is equal to 3 by 9. So that is the value of the given non-terminating recurring decimal expansion. If you want to simplify, you can simplify and write it as 3 1 the 3 and 3 the 9. Generally we expect you to write in the form 3 by 9, and I will tell you the reason why. Now the second example is a non-terminating recurring decimal expansion with a repeating block of 1, 2, 3, 4, 5. 1, 2, 3, there are 5 digits here. So take x as 0.12345 bar and multiply by 1 followed by 5 zeros into x will give you, that means the repeating block is made the whole part here, 12345.12345 bar, and then subtract x from the 1 lakh x here, will get 99,999x here equal to 12345, because this and this will cancel here, the decimal part gets cancelled, and we get 12345, and therefore x is equal to 12345 divided by 3, that is 5 nines here. And why I said to keep it 9 here, if there is 1 digit here, there is 1 9. If there are 5 digits here, there are 5 nines here. So therefore, it is a very easy conversion. If you are asked to convert 0.12345 bar, even without calculation, we can say the answer is 12345 divided by 90,999. So that is why I asked you to keep it in the form of 9. So therefore, writing in the form of 9, if it is a pure repeating decimal expansion, it's very easy to write in the form of 9. So please remember that. Now this is also a terminating decimal expansion, 100% a rational number. Now there are how many digits here? If you count the digits here, there are 21 digits after decimal point. So remove the decimal point, divide it by 10 raised to 21. So therefore we get that is the whole part here divided by so many zeros, that is 10 raised to 21 zeros here. So that is the p by q form, very simple. That is the p by q form of a given terminating decimal expansion of rational number. Now the fourth one, example number 4, to explain why 0.9 bar is 1. Very interesting, 0.9 bar is 1, that means 0.9999 is 1. So whether I write 0.9999 or write as 1, both mean the same here, or both are equal. Now let us understand how it is. Now let us take 1 upon 3. 1 upon 3 is what? When I go for long division method, I get 0.3333 unending or non-terminating recurring decimal expansion here. So multiply by 3 on both the sides. When I multiply by 3, it will be 3 into 1 by 3 is equal to 3 into 0.333 and so on. I will get 1 is equal to 1, 3 cancels here, 1 is equal to, multiply it by 3, I will get 0.9999 and so on, that is 0.9 bar I get. But what I get is in LHS I have got 1, on RHS I have got 0.9 bar, and therefore 0.9 bar is equal to 1, a simple way of proving it. This is one method. Now another method is, let us assume that x is equal to 0.9 bar. If x is equal to 0.9 bar, bring 9 as a whole part here. For that I have to multiply by 10. So 10x is equal to 9.9 bar. 9 bar cancels. When I subtract x from 10x, I will get 9x. 9 bar will cancel. I will get 9, and 9x is equal to 9. 9x is equal to 9, or x is equal to 9 by 9, or x is equal to 1, and therefore 0.9 bar, which is x here, is equal to 1. So the two simplifications which I have shown here explains why 0.9 bar is 1. So therefore another way of putting it is, between 0.9 bar and 1 there is 0 space. Therefore no number fits between them. Therefore we say 0.9 bar tends to 1, or 0.9 bar is equal to 1, or approximation of 0.9 bar is 1. So please remember that. Now coming to the fifth example. Now what is this fifth example? What is given is the decimal expansion of 1 by 7 has repeating blocks of 6 digits. That is what is given. Decimal expansion of 1 by 7 has repeating blocks of 6 digits and are cyclic. When multiplied by 2, 3, 4, 5 and 6, we get a cyclic pattern. Now we have to find out other numbers of the form 1 by n that have cyclic repeating blocks. That means already we have been given here as to 1 by 7, what is 2 by 7, what is 3 by 7, what is 4 by 7, what is 5 by 7 and what is 6 by 7. And there is a repeating block of 6 digits. There is 7 here, there is a repeating block of 6 digits and there is a repeating block of 6 digits. So you will find the digits are same, only they have been permuted or arranged in a different order. So we have 1 4 2 8 5 7, start with 2 2 8 5 7 1 4, and start with 4 4 2 8 5 7 1, and start with 5 5 7 1 4 2 8, start with 7 7 1 4 2 8 5, and start with 8 8 that is 8 5 7 1 4 2. So when you have 1 here, it starts with 1. When you have 2, it starts with 2. When you have 3, it starts with 4. When you have 4, it starts with 5. When you have 5 by 7, it starts with 7. And when it is 6 by 7, it starts with 8. And the same digits are repeated in the repeating block. So that is what is called as the cyclic repeating blocks of 1 by 7. But the question is, what are the other numbers of the form 1 by n that have cyclic repeating blocks? Now what you have to understand here is that 7 is a prime number, but it is not an ordinary prime number. It is a reptend prime number. It is a reptend prime. Now reptend prime means where 7 is a reptend prime, it means that when I take 1 upon 7, it gives us a decimal expansion which has repeating blocks of 6 digits, and 1 by 7, when you multiply by 2, 3, 4, 5 and 6, the repeating blocks are cyclic. So they are cyclic, and that is what is given to us. But now what are the other repeatant primes? Now so we have to take the other repeatant primes. The other repeatant primes are 17, 19, 23, 29. So if you take 1 by 17 for example, it gives us a repeating block of 16 digits, that is 17 minus 1, 16 digits. When multiplied by 2, 3, 4 etc. gives us cyclic blocks of 16 digits. So therefore whatever the pattern is seen for 1 by 7 is also seen for 1 by 17, seen for 1 by 19, seen for 1 by 23, seen for 1 by 29, and all these are called as reptend prime numbers, and the reciprocals will give us the cyclic repeating blocks patterns. So please remember this. So this is what is exercise number 3.5. The solutions of exercise number 3.5 is discussed. So go through this method of solving the examples, understand them and learn them, and write down in a book so that you can refer them whenever you want. Okay, good day. Thank you.